Welcome to The Explainer. I am absolutely thrilled to have you here today. If you've ever stared at a physics problem, maybe during a mock exam, and felt like it was written in some ancient, unbreakable code, you are exactly in the right place. Today, our goal is highly specific and incredibly powerful. We are decoding complex Cambridge IGCSE Physics 0625 past paper questions into a clear, structured masterclass. We're acting like alchemists today, transforming your raw, basic physics knowledge into absolute gold standard evaluation. You see, I constantly run into two types of students. Let's call them Alex and Sam. Now, Alex is super smart, but overloads every single answer with a massive brain dump of raw physics facts, but absolutely zero analysis. And then there's Sam. Sam rushes, completely misses the command word requirements of the question, and loses easy points. We are going to fix both of those problems today by looking exactly at what the exam requires.
Okay, let's dive into our syllabus roadmap. We are going to tackle this exam strategy in 5 distinct pillars today. First, motion, forces, and energy. Second, mastering thermal physics. Third, visualizing waves in optics. Fourth, solving circuit challenges. And finally, number 5, unlocking nuclear physics. Let's get right into it.
Section 1. Motion, forces, and energy. Mastering the mechanics of motion and matter.
Now, in this section, it's really easy to get bogged down by just trying to memorize a massive list of equations. This is exactly what our student Alex does. But physics isn't just about formulas. It's about applying those formulas to real-world scenarios. The most successful learners read a scenario, extract the vital data, and visualize the physical reality before they even touch a calculator. Let's look at a perfect example of this in action. Here's a classic kinematics challenge straight from a past paper. We have a roller skater making a journey, and we're given a speed time graph. The specific question asks, if a roller skater decelerates from 10 meters per second to 0 meters per second between the 60-second mark and the 100-second mark, how do we calculate the distance traveled? I want you to pause and think about how you would solve this. If you're like Sam, you might just guess numbers. If you're like Alex, you immediately start hunting for a complex acceleration formula. But when you have a graph, there is a much simpler visual decoding strategy.
Here is the absolute key to speed time graphs, and you need to write this down. The distance traveled is always equal to the area under the line. So let's break this down into 3 logical steps. Step 1. We look at the section of the graph between 60 and 100 seconds, and we identify the shape under the line. Because the skater is decelerating uniformly to 0, it forms a perfect triangle. Step 2. We apply the formula for the area of a triangle, which is 1/2 times base times height. Step 3. We calculate. The base is the time taken, which is 100 minus 60, giving us 40 seconds. The height is the starting speed, which is 10 meters per second. So 1/2 times 40 times 10 gives us 200 meters. Look at that. By visually decoding the graph, we bypass the messy algebra and turn a tricky physics problem into basic, foolproof geometry.
And this brilliantly illustrates another core concept in our mechanics section. Take a look at these metal masses. They are clearly different sizes, which means they have different volumes. And because they are different sizes, they obviously have different weights and masses. But the source material tells us they are all made from the exact same material. So, what physical quantity is perfectly identical for all of them? If you said density, you hit the nail on the head. Density is an intrinsic property of the material itself, calculated as mass divided by volume. No matter how much you scale the object up or down, the ratio of mass to volume for that specific metal remains perfectly constant. And understanding how to state that clearly is exactly how top students structure their answers. Before we continue and reveal exactly how to structure those perfect answers, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's move on to Section 2, Mastering Thermal Physics, from hot liquids to cool solids. In the last section, we were dealing with macro-level motion, right? Roller skaters and heavy metal weights. Now we are shrinking our perspective all the way down to micro-level atomic behavior. To truly master thermal physics, you need to be able to vividly imagine what invisible particles are doing when heat is added or removed from a system. Imagine this incredible industrial scene. We have workers pouring molten, incredibly hot liquid metal into a mold where it will eventually cool down and solidify. Obviously, there is a massive temperature change happening here. But exam questions rarely ask you just to describe what you see with your own eyes. They don't want a surface-level answer. They want to know what is happening microscopically. As this metal cools and transitions from a liquid state to a solid state, an incredible atomic transformation is occurring, and we need a strategy to explain it. This is where I like to introduce the Peel framework: point, evidence, explanation, link. It's how we guarantee we hit the examiner's marking criteria.
So the crucial point here is knowing exactly what the examiner is looking for when you are commanded to describe this change of state. You can't just say, it gets hard. You need to hit 3 very specific criteria: arrangement, separation, and motion. Let's apply our strategic thinking here. First, the arrangement. In the hot liquid, atoms are somewhat random, but as it cools into a solid, they shift into a regular, fixed lattice structure. Second, separation. While liquid atoms are relatively close, solid atoms become very, very closely packed together. And third, motion. This is the big one where students lose marks. Liquid atoms can move freely and slide past one another. But as thermal energy drops and it becomes a solid, those atoms stop moving freely and begin to only vibrate in place. If you systematically list these 3 changes, taking your answer from a messy paragraph to a structured list, you literally guarantee top marks.
Moving right along, Section 3. Visualizing waves and optics. Decoding the electromagnetic spectrum.
Here, we are decoding how energy travels through invisible waves all around us. The trick to this section is remembering that everything from the visible light we see with our eyes to the Wi-Fi we use for our phones is part of the exact same continuous family, the electromagnetic spectrum. I want to give you a quick interactive challenge right now. This is where we see red pen marks transform into green check marks. The syllabus requires you to connect these invisible phenomena to highly specific practical applications. We have microwaves, infrared, and X-rays. I'm going to give you a few seconds. In your head, try to match these 3 types of electromagnetic radiation to their real-world uses: detecting broken bones, satellite communications, and detecting intruders at night. How do their specific wavelengths make them useful for these tasks?
Let's reveal the answers and see how you did with your mental matching. X-rays are used for detecting broken bones because they have a high enough frequency to pass right through soft tissue, but they get absorbed by denser material like calcium in your skeleton. Microwaves are absolutely vital for satellite communications. Why? Because their specific wavelength can pass straight through the Earth's atmosphere without being absorbed or reflected by clouds. Infrared is essentially thermal radiation, making it perfect for detecting the body heat of intruders at night. We also have gamma rays on this spectrum, which are highly penetrating and used in targeted medical treatments, and visible light, which famously ranges from red to violet. The position of each of these in the spectrum depends entirely on its frequency.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, Section 4. Solving circuit challenges. Currents, components, and clean energy.
Now pay close attention because electricity is traditionally the area where learners lose the most marks. Why? Because the rules shift completely depending on how the circuit is built, and it's so easy to get confused. Let's do a little interactive Find the Flaw workshop here. Let's contrast the 2 fundamental ways to build a circuit. In a series circuit, there is only one single path for the electrons to flow. This means the current is exactly the same through all components, but it has a fatal flaw. If one component, like a single lamp, fails, the entire circuit breaks. A parallel circuit, on the other hand, is built with multiple branches. The current actually splits across these branches. This is incredibly useful because it means if one lamp blows out, the others stay on, and components can be controlled independently with their own switches. Understanding this difference is the absolute bedrock of circuit analysis. If you ever write that current splits in a series circuit, an examiner will mark you down instantly.
Now, what's really interesting about this next slide is how we take those microscopic concepts of electron flow and scale them up to massive, real-world national power generation grids. Look at these wind turbines. The physics syllabus doesn't just want you to calculate simple resistance on a piece of paper, it completely expects you to evaluate how we generate the electrical energy that powers those circuits in the real world. We need to be able to scan this concept and extract the core trends.
Let's do a speed writing challenge. When an exam asks you to compare wind turbines to fossil fuels, you need to provide a balanced, structured argument quickly. Here is the concise summary you need to memorize. The 2 primary advantages are environmental. Wind is renewable, meaning it literally will not run out, and it produces absolutely no greenhouse gas emissions or atmospheric pollution during operation. However, there are very real disadvantages you must include. The biggest one is unreliability. Turbines only generate power when the wind is actually blowing at the right speed.
Secondly, they can cause visual or noise pollution for local residents. Hitting these exact practical and environmental trade-offs without rambling shows the examiner you see the full picture and gets you maximum points.
Let's see how this builds into one of the most important concepts in all of physics, electromagnetic induction. If you are asked to describe an experiment proving induction, you need a perfect Peel paragraph. Follow these steps perfectly. Step 1. Connect a coil of wire to a sensitive ammeter, forming a complete loop. Step 2. Take a permanent magnet and physically move it in and out of the coil. Step 3. Observe the needle on the ammeter. It will deflect, proving that simply moving a magnetic field across a wire induces an electromotive force, or EMF, creating a current. This simple, elegant motion of a magnet and a coil is exactly what is happening inside the giant generators of those massive wind turbines we just looked at.
We've made it to the final boss, Section 5, Unlocking Nuclear Physics, Half-Lives and Radioactive Decay.
The very word nuclear makes people nervous, but I assure you it is just about following a few highly predictable, logical rules. It's essentially a game of probability and atomic math. Let's look at one of the most common ways this is tested. Here is raw data from an actual past paper scenario. Let's do a quick data scan. A scientist is measuring radiation over 24 days. On day 0, the detector reads a total count rate of 200 counts per minute. On day 24, it reads 50 counts per minute. The question asks you to calculate the half-life. The trap almost everyone falls into, especially students who rush like Sam, is just dividing 200 by 50 and getting it completely wrong. Why? Because of background radiation. You must remember that the environment naturally emits radiation. In this case, 40 counts per minute that has absolutely nothing to do with our sample.
Here is the absolute genius method to avoid that trick and lock in your marks every single time. Step 1. Always subtract the background radiation first to find the pure sample count. So 200 minus 40 is 160, and 50 minus 40 is 10. Step 2. Now we count the half-lives it takes to go from 160 down to 10. 160 halves to 80, 80 to 40, 40 to 20, 20 to 10. That is 4 distinct half-lives. Step 3. Divide the total time by the number of half-lives. 24 days divided by 4 means the half-life of this specific isotope is 6 days. Follow those 3 steps and you will literally never miss a half-life calculation again.
Before we leave nuclear physics, we absolutely must contrast the extremes of radioactive emissions, alpha particles and gamma rays. Examiners love asking about their properties, and there's a brilliant inverse relationship you have to remember. Alpha particles are relatively massive and carry a +2 charge, giving them a very high ionizing ability. They smash into other atoms and steal electrons easily, but because they do this so aggressively, they lose their energy fast, meaning they have very low penetrating ability. A simple sheet of paper stops them entirely. Gamma rays are the exact opposite. They are waves of pure energy with no mass and no charge. This gives them very low relative ionizing ability, but extremely high penetrating ability. They can pass right through the human body and require thick lead or concrete to finally stop them.
V-synthesis, bringing it all together for exam day. We've journeyed all the way from macroscopic mechanics down to the vibrating atoms of thermal physics, through the invisible waves of optics, into the flowing electrons of circuits, and finally into the decaying nuclei of atomic physics. The topics vary wildly, but the system of decoding physics does not. To guarantee top marks, you need 3 rules. Number 1, command word decoding. Number 2, applying frameworks like Peel. And number 3, strict time management so you don't rush. If there is one ultimate anchor for understanding almost every system we've talked about today, it's this quote right here, straight from the source syllabus. The principle of conservation of energy. Energy cannot be created or destroyed, only transferred. Whether it's the gravitational potential energy of a roller skater turning into kinetic energy, the kinetic energy of the wind turning into electrical energy in a turbine, or the nuclear binding energy released as heat in a reactor, it is all just energy changing costumes. Remembering this principle gives you a massive advantage when analyzing any unknown physical system in an exam.
Remember, if you master the core principles and decode what the question is truly asking, the math will naturally follow. You now have the absolute blueprint to analyze speed-time graphs, explain atomic states, evaluate energy production, and untangle half-lives. Keep visualizing the science behind the numbers, and those complex questions will become crystal clear. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams, your Cambridge success starts here. Keep learning, keep exploring, and I will see you in the next explainer.